Good evening and welcome everybody. This is Obi-Wan Pez4 and Simplex Pachinko. We are going to be doing some math tonight. And I'm going to pick up a little bit from where we left off last time. Ugh, so much pollen. So I found, when we were talking about hyperbola, this was a specific hyperbola which had foci at plus or minus 3, 0, and the difference, as we were talking about with the hyperbola, between the focal lengths to whatever point we're at. So the difference between the sizes and the focal lengths is always going to be 2. So we were able to say that when our point is like directly in line with our foci, that their sum ends up being 6, their difference ends up being 2, and we were able to figure out that here, okay, clearly that's going to mean that a is equal to 1. So our a value, the yep, the a value, which is the vertical stretch factor, no, that's wrong. This time it is the horizontal stretch factor. Also, in this case, I don't think we actually had a specific term for A, unlike the ellipses when it was semi-major and semi-minor axis. Nope. Well, anyway, this is a effectively dampening factor to the x values. So if it dampens our x values, that means our y values will be smaller than we expect if a is big. So yeah, that is as similar to a vertical stretch factor as we're going to get. Okay, then we said that we're going to get this particular setup if we draw a triangle between any particular point. That's not true. Okay, we drew a point from the center at 0, 0 out to the leading edge, our vertex, which was at a, 0. And then I was trying to have a fight that our C value was not obvious. The distance between the center and the focus was actually identical to the center out to a, B. So we knew that 1, B was going to be on the hyperbola. So we plug in 1 here. We end up with a 1. That subtracts off, becomes 0, and y is 0. Okay, that was not what I wanted. Okay, well that's true because that's this point here. Okay, never mind. So 1, B was not on the hyperbola itself. Interesting. Okay. oh no, 1 comma b is that value, which is the corner of the rectangle that we use, which connects the vertices on both sides. They are the middle of the vertical sides of our rectangle. The horizontal sides, allegedly, are at height b. Now I'm trying to remember why I realized it was obvious. So this will make a right triangle. But why is that true? There must be like some sort of trig reason, right? Alright, gonna have to rehash this. 'Cause Alright, when we did it, we found that b was going to be equal to 2 root 2, so b squared was 8. So this got us the equation of the specific hyperbola that we were looking at, x squared minus y squared over 8 equals 1. Alright, why is that true? Why is it true that focus is going to go through this point here? Wait. Not that point there. It's close, but it's not quite that. It's along the asymptote. So it's that point right there. Why is it true? Very not correct, but no, actually it's not that. It's not that incorrect. And then we could just manipulate it, so no one will notice. That's fine. Totally looks 100% real. That looks pretty good. We could pretend. Right, why is this going to be C and this is going to be C? Right, so we got to prove that. This is not a point on the thing. This is a point on here. That's labeled A, 0. It is our vertex. Nice of the ad break notification to come in. Jeez. 17 minutes. Okay. So it's a distance of c from 0 to the focus, which is given. Right? We defined that as the focal length c. And then we said that a is going to be the distance that we travel from the origin, 0, 0, out to a comma 0. Right? Granted. And that is where the vertex is. So we've shown this on multiple occasions. That's actually the distance that it's going to go. Now the question is, how do we prove that that is actually C? This is a right angle. I mean, I kind of want to make this and go with similar triangles. As ridiculous as that might be. This point is x comma y. This point is c comma we don't know what that is yet, but we can figure that one out probably pretty easily because we know what the slope of that line is going to be. At least allegedly. That's not x comma y. Don't do that. Right, because this is not actually on the hyperbola. Right, this is a comma what? This is also a right angle. Well, that's not helping much. Now we said it's a comma b. Is that necessarily true? Probably yes, but not the point. So if x becomes extremely large, what is y in terms of other stuff? I know that this is kind of a dead end, but y is equal to, that's going to get us a square root. And we're only in the first quadrant, so we want the positive one. This is going to end up being b over a squared x squared minus b squared. And if x is equal to, no, that's the ellipse, so we're still going to get 0 here. do we find the asymptote? Oh, yes, okay, okay. So if we take the limit as x goes to infinity of this thing, right? B squared over a squared, x squared minus b squared, then y will approach b squared root b squared over a squared times x squared, which is going to be equal to b over a times x. Now I am saying that it is approaching these values. It is not actually that value, right? So we're starting to get, you know, when we're dealing with limits, we're talking about what's happening to the overall structure that's going on here. So this interior portion, you notice that this minus b squared, if x is really tremendously large, then this minus b squared is going to have practically no effect at all. So if we are thinking about like what is it doing, then we can kind of ignore the minus b squared when we're talking about values of x which are approaching infinity, which are getting so ridiculously large that, you know, what's going to happen overall. So x squared is much bigger than some constant if x is getting close to infinity. Right, so y is going to be approximately b over a times x. Therefore, well, slope of the positive asymptote anyway, which also means that this whole thing here, y is going to be equal to plus or minus b over a times x, is going to get us the equations of asymptote. Okay, so the equations of the asymptotes, y equals plus or minus b over a times x. Okay. And if, right, if this is a, then that question mark here can definitely be explained. We can find the y value, which is definitely going to be b. Right, so y equals plus only in this case b over a times a, x equals a, y equals b. So that's a point. Then when y equals plus b over a times c, then we end up with x equals c, y equals bc over a. So here, this is going to end up being bc over a. Okay. Now with that, we want to prove that a squared plus b squared equals c squared. And actually that c value. Right, we don't know that this is technically a circle. So right, that's c comma 0. That one is a comma 0. does a squared plus b squared equal c squared? It certainly is equal to c when a is c. Right, is this actually going to form a circle here? The contention is yes, that it's always going to end up being a circle, that a squared plus b squared equals c squared for this particular shape, which also means that man, I don't even know. Okay, so we do have so we have B here, have B, C on A here. So the scale factor is C over A. From orange to blue. So what does that tell us about? Okay. Let's try it this way. We want to find what we want to find out what we get when we do c squared plus bc over a parentheses squared. What do we get, right? This is going to be c squared plus, okay, that's not really helpful. All right, b squared c squared over a squared, or maybe, hey Zach. So we're still doing the GRE stuff. This is still looking at the hyperbolas. I'm just trying to figure out if we can prove that a squared plus b squared equals c squared for the c being the focal length and a and b being our horizontal and vertical scale factors, or horizontal and vertical distances. So I'm not saying I'm skeptical, but it's one of those things. I'm not 100% sure that that's true. So I want to just prove it to myself, I guess. C squared times 1 plus b squared over a squared, which kind of seems interesting. Alternatively, we could just leave it the way it was. As in the following. Yes. Yes. Linear eccentricity c, which is also the distance to the focus from the center, or either of the foci from the center. right? So the white circle that I've put in there is speculation, right? Is C actually the radius, which will then, again, we know the answer is yes, but it's just a matter of actually proving it. Unless I'm missing something really obvious, in which case, go ahead and spoil that for me. All right, so we want to scale this down. If we scale this down, then c squared plus b squared c squared on a squared is going to then be multiplied by a over c to get a squared plus b squared. Right, we know that this distance is a here, we know this distance is b here, and so we're trying to find what is that diagonal a squared plus b squared going to get us. We know it should be c squared. But this is going to be ac plus p squared c on a. That's really ugly. And it doesn't contain a c squared, so that's good. Hum. So the next part is showing that all of this is equal to c squared, which I'm sure 100% works. It has to. No, it's literally just c over a times a squared plus b squared. So yes, that's true, but that doesn't actually prove. It just proves that a squared plus b squared is equal to a squared plus b squared. Ooh, wait a minute. Times the scale factor c over a. Okay, maybe we're not allowed to do that. Hang on. That definitely can't be true then. So that's weird. What am I missing? C over A multiplied by. This will get us a squared. And and this will get us b squared. I did something wrong here, because otherwise this doesn't make any sense. Right, this implies that c over a has to be 1, which is not true. Alright. Or, again, c over a times a squared plus b squared. But none of this is helping. So essentially what this is saying is that if we want to end up with a nicer version of all this stuff, then like things are going to have to go away. That doesn't make any sense. Okay. Again, not really working. AC plus b squared c over a is equal to c squared plus b squared c squared over a squared. Oh, gross. it's the same thing. Only in this case, c is equal to c squared. So c has to be 1, but that doesn't actually make any sense for what we're doing. Right, generally speaking, c does not have to be 1. Oh, no. Never mind. That's not what that says. I don't think it's helpful, but... This is AC times 1 plus b squared over a squared, which is equal to c squared. Okay, now a has to be equal to c, which means c has to be 1. Never mind. And none of this works. Right. A does not always have to be equal to c, and in fact, can't do that. So there's something wrong with my assumptions in here. Alright, the asymptotes are linear. Grr. Yeah, I think I'm going to have to just be unsatisfied on this one and then figure it out later. So, oh well. All right. We have the division, remainder, and factor Theora. So we're going to go with division. Well, technically it's a division algorithm first, but it's all good. In previous sections, we already said that if we have some polynomial, p of x, which is equal to, we have numbers out front, our coefficients, which are going to be a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus all the way down until we get plus a1x plus a0. Right, for all of these. Zeros of the polynomial. You know what? Not even zeros. We may divide polynomials into p. So if p of x is equal to 7x to the 6 minus 3x to the third plus, let's do minus just for the hell of it, x squared minus 5x plus 6. Right, if we take this and then we say we've got a small polynomial, actually let's just call it a different polynomial, q, then this one might be like x squared plus 7x minus 3. And if we want p over q, that's going to be our 7x squared minus 3x to the third minus x squared minus x to the 5x plus 6 all divided by x squared plus 7x minus 3. These are not factorable. At least that we know of. However, we can use the division algorithm. This is x squared plus 7x minus 3 divided into here 7x squared minus 3x cubed minus x squared. You might be screaming right now. It's all right. Don't worry. I got it. All right. So looking at this stuff, what we would like to do is get rid of the highest degree term, and then the rest of the stuff we're probably not going to be able to subtract out very nicely. So it's going to just have to wait until future rounds in this algorithm. So right now what we want to do is look at the highest degree term in both and say, how do we get from x squared up to 7x to the sixth? How many times can we subtract off the definition of division, right? How many times can we subtract off the divisor on the outside from the dividend on the inside? So our dividend being the large 6th degree polynomial p, and our divisor being the small 2nd degree polynomial q. Well, we can subtract x squared from x sixth, right? An infinite number of times will not actually get it to x to the sixth, because x squared is so much smaller. However, if we multiply x squared by x to the fourth, so we subtracted off x to the fourth times, then our x squared multiplied by our x to the fourth becomes x to the sixth. And now we can compare the same types of things. So here we look at this and we say, all right, same types of things. X squared times x to the fourth is going to get us x to the sixth. We want to engineer this such that this term will go away. We need that to be a 7. So how do we get that to be a 7? Well, we got a 1 out in front of the x squared, so that's no help. But then we can multiply our x to the fourth by 7 in order to get the same thing, 7x to the sixth. We are engineering this to get rid of that first term. The rest of it is going to be along for the ride. So now we look at this and we say, okay, this is 7x to the fourth times the whole divisor. Right, let me not do that. Okay, so we want to multiply 7x to the fourth times 7x. So this is going to be a positive 49x to the fifth. Then we multiply 7x to the fourth times negative 3, and we get a negative 21x to the fourth. Okay, and then again, because we're dividing, we're trying to figure out how many times can we subtract this from that thing, right? That's 7x to the fourth. Our 7x to the sixth minus 7x to the sixth is going to be 0. It was engineered this way. Then we go to our next terms. Well, if we look at it, this is 3x cubed minus a 49x to the fifth. These are not the same things. So we can't compare these two polynomials directly because, again, literally there's just no like terms there. So what do? Well, easiest thing to do is to say, I see, we are trying to trick ourselves. Let's move this down a bit. And say, all right, look, we didn't have GRE. Looks like moths are coming in the... No, I closed that. Okay, never mind. We don't have any x to the fifths. We don't have any x to the fourths. The next term that's going to be useful in this is going to be x to the third. That'll be on the next round. So, not right now. Okay, we've got 0x to the fifth minus 49x to the fifth is going to get us a minus 49x to the fifth. Okay, and then a 0x to the fourth minus a negative 21x to the fourth is going to be a positive 21x to the fourth. Okay, so now we look at this and say, how many times can we subtract? How many times can we subtract x squared from negative 49x to the fifth? Well, we just did that in the above part, right? What do we need to multiply by? What do we need to multiply by x squared in order to engineer our first term to just go away? Well, this has got to be a negative 49x to the fifth. in order to make sure that this term goes away. Again, we're going to subtract all of the following. So we now say, how do we get this? Well, x squared times x to the third is going to get us up to x to the fifth. And then we just need to match the coefficient that we're given. So we have a 1 out in front of the x squared. It's going to be a negative 49x cubed in order to get us a negative 49x to the fifth when we multiply those terms together. Then again, we're just going to multiply the rest of the divisor by negative 49x cubed, and then sweep out the rest of these numbers, or subtract them anyway. That is a 7 times a 49, which is a 343. Yeah, 343 in the negative times x to the fourth. Okay, a 3 times 49 is going to be 3 times 50 is 150 minus 3 is 147. Okay, and then that is a negative times a negative, which is a positive. What did I say? 147 x cubed. Okay, now if you notice, we have an x cubed term here, but we don't really have one here yet. But we do have one there. So bring this down because it's going to be used on this round. Okay, so negative 49 x to the fifth minus negative 49 x to the fifth is 0 as intended. This is now going to be a 21 x to the fourth minus negative 343 is a plus. So 364 in the positive x to the fourth. Okay, same deal again. This is going to be a negative times the 147 is negative 147 minus 3 is going to be negative 150 x to the third. And since this has 3 terms, we're going to go down one more. So 4, 3, 2. So we get minus x squared. Okay. Again, how do we get 364x to the fourth to go away? We need to multiply x squared by something in order to get this. So again, 364. And we need 2 more x's, so x squared is going to get us 364x to the fourth. We're subtracting all of this stuff again. This is going to now be a 364 times 7 is 21, 25, 48. 25, 48. X cubed. This is in the positive. And then negative 3 times 364 is going to be 900, 1,080, 92. X squared, and that is in the negative. Again, subtraction, going to get us 0 for the first one. This is going to get us a negative 2548 minus negative 150 is going to be a 2698 in the negative. X cubed. This is a negative 1x squared and a plus negative 1092, so that's going to be a 1091 x squared. Okay, and then minus 5x. We're going to bring down the next term. Almost in the home stretch. We need a negative 2698 x. In order to make that work again, x times x squared is going to get us x cubed. Ugh. Gonna have to do that in my head. Okay, so I guess. Hey, I've got an abacus here. Actually, technically it's a sort of not an abacus, but nonetheless. We'll do that one out. Ads are about to start, so we'll be back in 3 minutes. And thank you everybody for stopping in. My name's Obi-Wan Pez. We'll see you in a little bit.
Indeed can help her find great people fast. I need Indeed. Indeed you do. Sponsor a job on Indeed to unlock more tools that save you time and help you hire quality candidates. To start hiring, visit Indeed.com/try today.
We're doing some Tai Chi today. Might as well practice a little bit. So we have some pretty decent warm-ups that we do in the class. So I talked about this before, but basically you're letting your arms kind of fall as they may, but then every time that they get toward the bottom, you give them a little boost, like pushing a kid on a swing. And like literally just this little tiny boost here is going to give a lot more energy into your arms. Let them swing. Drop your body, and then as they're coming up, you're also bringing your body back up. And it increases the flow of all the fluids that are in your arms and shoulders especially, and usually leads to like less soreness and stuff like that, so it's helpful. He also has us do like front and back as well, So we're just doing this. Again, increasing all of the blood flow, all of the other fluids that are in there. Help keep your joints nicely lubricated as you're doing stuff. And then switch. Just rocking back and forth. And again, letting your arms just kind of fall. And as you start rocking back and forth, they just gain more kinetic energy, which translates into potential energy. So they go higher. Right. So our Tai Chi form stems from a couple of basic motions, and our instructor, I finally met like one of the other ladies who's doing Tai Chi. This is the first time that we have had a class together, so it was pretty cool being able to actually meet up with some other people who are doing it. So we had started on the other side of the room, and we start with keeping your tailbone, the coccyx, kind of down underneath yourself, and at the same time not beyond the halfway point of your calf. And you can actually feel it, like if you're pushing forward on your front leg and you're pushing back on your back leg, then you're kind of holding yourself in a little bit of tension. And then if you let go with your front foot, it kind of, like your body wants to move forward because you're still pushing off of your back leg. Usually not quite as exaggerated. What can you do? So while you're doing this, the key is then we have a couple of different moves that we actually do. So the first is push. So you use your hands, kind of cup them together a little bit, and then separate your hands as you stop your forward momentum and sink back. And then the next one is going to be a straight push. So this is just coming out with your palms and then putting them together. On the next step, it's just going to be another push with the back of your hands and then separate out and then come like that. And then we just go back and forth and do that a whole bunch. Reason being, this comes from the actual form that we learned. I learned it basically the first time that I went to go see him. Because again, he was like, well, you already know karate, so yeah, it's fine. So from kind of neutral position, again, get your tailbone underneath you, engage some of the muscles, get your feet actually pointing forward, which is one of my problems. We come up, push, just gently push out with the hands, and then we push down. From here, there's a way that we do things in Tai Chi where we kind of bring a ball of energy with us, and we come out this way, and then go into a ward-off position off to the front, which then gets us into our back leg being locked position. This also allows us to keep this frame. I've been talking about, like, some of this is a little bit like ballroom dancing, where once you have this frame, like, there's a lot you can do with it, and it just ends up like too long. Not quite wide enough. All right. Once you have this frame, then there's a lot you can do with it. So typically you're going to just like be able to use this and move the whole body forward. And there's not a whole lot of, like, somebody would have to struggle to stop you most of the time. So once you have this ward off, which again, you're going to be using like the back of your arm to deflect anything that might be coming your way. And generally speaking, again, keeping a nice frame, pushing again into the floor with the back leg, keeping your coccyx no further back than halfway down your calf. And I'm going to say thigh earlier. That's embarrassing. Now we come further to the right, sink into the hip here, and then we leave this right hand where it is, come back just a little bit, bring them both this way, go into a push, and then release, sink back, and then we're back in a neutral position. And then from here, there's a bunch of stuff that you do, but we haven't learned it yet, so what can you do? But we just basically do this all at once. Then we're also supposed to practice it on the left-hand side as well. Yeah, I never really got it. And then I started doing karate. It's like, oh. My spouse and I took ballroom dancing for a while. Had a dance that was choreographed for our wedding. Okay. So this is 2698. And we want to multiply by 7. Fun. Yeah. It was the same for us. Yep, had the just started taking ballroom dancing with our Parks and Rec, and then we ended up engaging her for that choreography. So it was actually fairly inexpensive overall. She was like, a few $100s for like choreographing a dance for us and giving us private lessons in order to learn it properly. Okay, so this'll work. I think that should be it. Yeah. Okay, so the way I have this set up is that you start all the way on one side, and let's carefully not shift these too badly. Right, so you start with the number you're multiplying by. In this case, I've got 7. So the way the Sotoban works is that the top bead is worth 5, and then each of the bottom beads are worth 1. You'll notice that we have 4 and 1 as the two sections of beads. So we have 4 1s beads and 1 5 bead. The Chinese abacus will, on the other hand, have 5 1s beads and 2 5s beads. This makes it a little bit nicer, just so that you can do a little bit of trading off without having to do as much like mental arithmetic, which it's fine, but some people have some issues with them. So this is a replica of the Japanese Soroban rather than the Chinese abacus, but it's it's kind of like, it's the same stuff. It's just, do they have the extra beads in order to carry over, or are they just trusting you to be like, nah, it's fine. Over here we have, you see here we have 2, and this is going to be in the thousands position. There's also a little tiny white dot here, which tells us that this is the first one in the thousands position. That's not true on this one, is it? Oh, no, it's the black dot. So we have these black dots in the middle of the white. You can't actually really see it. It's too bad. You can sort of see them here, and here, and here. Is that... No, that's not doing anything. Okay. But anyway. So we've got 2,000, 800, nope, 600, man, 98. So the way that you multiply on a soroban is a little harder, but it's all right. We're going to destroy the evidence of the number that we have here as we make it. Now, it is also possible that you could leave a gap here and say like, okay, look, I'm going to need, I've got 4 numbers here, I'm multiplying by a 1-digit number, so I'm going to need at most 5 digits, which means I could translate this down here and say that, you know, we can use these 5 or potentially these 5 instead of having these 4 here. But it's not a big deal. We can also, like I said, destroy the evidence as we're using it, which sometimes is a little bit of a pain, especially when you make a mistake. So first few times you do this, it might actually be worthwhile, like, not to use the abacus as both your workspace and also your like memory storage of what you're multiplying. But we're going to do it, just it'll work. So here we're going to multiply 7 by 2. It gets us 14. So we're going to start from here. This is going to be 4, and then this is going to be 1. So 14. We start at the end of the number, and then we work our way down as we move. This does work if you multiply by 2 or 3 digit numbers, but it gets a lot harder. So it's just a matter of like, what numbers are each of these things going to affect? And then you affect only those numbers, only those columns, until you get everything that's going to affect that column done, and then you move down one more. So we're done with this. We got our 14 out of the 7 times 2. So we move down 1. This is now a 6 times 7. 6 times 7 is 42. So here we're going to replace that 6 with now 2. And then we have to add 4 to the next one up. So again, 6 times 7 was 42. So here we have to add 4. I can't add 4 because the bottom 4 are already engaged. So instead of adding 4, I'm going to add 5 and subtract 1. So when I add 5 and subtract 1, now I've got this number here. So that is an 8. We're done with the hundreds. So now we're going to move to the tens. The tens are, again, a 9 times 7 is 63. So we're going to clear the rest of those and make 3. And then here we need to add a 6. We can add a 6 here in the hundreds place because we can add a 5 and a 1. That's pretty nice. Okay, and then we move down to the ones position. This is an 8 times 7 is 56. So here we get rid of those two and make a 6. And then we need to add 50. So we do it here. Now we get a number which is 10,000. Right, 5, 6, 7, 8. So 18,000. 800. Wow, 18,886. 18,886. Am I correct? Sure hope so. 2698 multiplied by, that was 7. 18,886. Awesome. So we're going to go over and back to Math Night. 18,886. What was that? So minus, okay, minus 2698x cubed. This is now going to be a minus 18,886x squared. Keeping in mind, right, this is a GRE. Everybody's probably good enough to do this. That's going to be a 3 times 2698. So with the Sorbonne, like the abacus, easy etch-a-sketch method of getting rid of the numbers, or you just tilt until everything falls down. That engages all the 5s. You don't want that, so you stick your finger on the bar and then just kind of move across, and it disengages all of the 5s. Okay, so 2698, right? 2698, cool. And then we're multiplying by 3. So we multiply a 2 by a 3, and we just end up with 6. We have here a 6. Multiplied by 3 is 18. So that gets us an 8 here, and it adds a 1 to the next column. 3 times 9 is 27. So here we have a 7, and we add 2 to the next one up. Problem: we don't have 2 left here. So if we can't add 2, we can, on the other hand, add 10, bring a bead up, and subtract 8. So minus 5 minus 3. That's a 0 in this column now. We're done with that one, and then this is an 8 by 3 is going to be 24. So that's a 4, and then we add 2 to this column here. So we have now an 8,094. 8094. 2698 times 3. 8094. Awesome. This is a plus 8094x. And then we are subtracting this whole row. And then we get, so this is a 0 engineered that way again. Here, this is a 1091 subtracted from is added now to 18,886 is going to be 19,977. And then this is going to be a negative 5 multiplied by, you can't see that, negative 5 subtracted by 8,094 is going to be a negative 8,099x plus 6. Right. And again, this last number here is going to provide the information as far as what we're going to do in this last one. How do I know it's the last one? Once we're out of whole numbers, then we've got to get fractions, but like we're not going to have fractions. Especially since this is, or at least we're not going to have that kind of fraction. We're going to have a fraction in the sense that we're going to have a remainder and we're going to have the divisor. And when we bring the remainder and divisor together, that gets us the like remainder fraction that we're going to get for this division. Okay, So 19,977 x squared. And then the next term is going to be positive. 19,997 plus, 19,997 times 7, which we could also do as, this is 20,000 minus 23 times 7. So this is a 140,000 minus 161. So 139, 839. 139,839x. Okay, and then this is going to be same thing here, but times 3. Is going to be 60,000 minus 69, which is going to be minus parentheses. Minus 59,931. So now this is going to get us, again, 0x squared, as we knew was going to happen. And then we get a 8,099 plus negative of all of it. 8,099 plus 139,839. So this is going to give us 8,000 is going to be 140 negative 147, and it's not going to go over 1,000. 800 plus a 1 from the next one is 900. 20 and 1 from the other is 38x. This is now going to be negative is a positive. 59,930. 1 plus 6 is 7. So now we've got those terms. Ugh. Right, this is now in the way. Minus 147,938 all x plus, that's not going to work, plus 59,937 divided by x squared plus 7x minus 3. I think so, right? Yep. Okay, so realistically, this should either be that this is going to be a plus this fraction with the negative on the 147 explicitly. $147,000 explicitly. Or we could make it a minus the whole fraction with this positive number first and that negative number second. 59,937. 47,938x over x squared plus 7x minus 3. So it's kind of up to you which way you want it. Maybe your teacher will actually care, but for the most part, nobody's going to care. It's fine. As long as it is, an appropriate answer. As long as it is an appropriate answer, yeah, nobody's going to really fault you for having a maybe slightly different form for it. Unless they're just being jerks that day. Sometimes that happens. But you know, don't be mean to them. Maybe they're just having a rough day. Alright, super ugly, disgusting, all that good stuff. But it's a good way of like getting practice for this, is just make up a problem, and if it turns out that it's really ugly, then, you know, you've been getting some other arithmetic practice in, and it should be all good. The remainder theorem is super cool. So what this says is that when you have P over Q, trying to remember exactly what the wording is so that I don't accidentally paint myself into a corner again. Right, so let's actually discuss this part here. The division algorithm. So we got P over Q like that is going to be equal to the quotient little q of x for quotient plus the remainder divided by our q of x, which is also the divisor, so which also means that p of x is equal to little q of x, the quotient, multiplied by big Q of x, again the divisor, plus r of x, the remainder. You do have to have the usual caveat here where big Q of x cannot be 0. Something that gets you 0 in the denominator isn't going to work, so we just can't let that happen. Right. This was the remainder theorem, yeah. Almost knocked over my coffee. So this is... for linear factors Q. I don't think so. Was it combinatorics? And or how messy did it get? Okay, so for linear factors Q, elementary math educate, nice. I don't know that I saw that one. Yeah. um, so linear factors Q, which are going to be as divisors x minus k. So if you need to, you can factor out whatever other constants you have to in order to get x by itself in the, well, 1 times x as the first part of this term. Not that it really matters, because it's, it's all good. But you do have to get... no, it does matter. Never mind. Because you have to factor out any leading coefficients on x, because that will affect k. Okay. Then using this stuff from below, p of x is going to be equal to little q of x multiplied by x minus k plus r of x if we plug in k value, ta-da! Right, p of k is going to be equal to, what's q of k? I don't know, and quite frankly, I don't care, because k minus k is going to be 0. So this is now gone. And then we just get r of k left over. So this says that p of k is going to be equal to r of k. The actual polynomial value at k is going to be equal to the remainder at k. So if we were to go back, no, actually we can't do that one because that's not a linear factor. That's a quadratic factor. I don't think that actually matters. It doesn't matter. Well, no, okay. Okay, no. We would have to find the value at the 0 of that particular polynomial. So I don't want to do that. But we could say, if we wanted to take p, which was that. Control C. And go over here. And Control V. Woo! Okay, so that's p of x in this particular case. If we want to evaluate p of negative 5, like, I don't really want to do that. It's not like it's horrendous, right? We could still plug in the values, but this is going to be, negative 5 to the 6th power times 7. I'm going to want a calculator, quite frankly. But if I want to just get a quick number, can I do this by hand? then the answer is yes. We could easily go through and say, all right, we had talked about synthetic division before, where we could say we want this is x plus 5 is equal to 0. So we're saying that x is equal to negative 5. If we're dividing through by the factor whose 0 is negative 5, then what we can do is say, just like we did for the long division one, we're going to write down coefficients only. So this is x to the 6th, x to the 5th, x to the 4th, x to the 3rd, x squared, x constant. We're going to need more room, I think. Because we're going to multiply by negative 5 a lot. This is going to get kind of messy, but it's fine. What we do is we say the first term, we're going to multiply up a 0. So, like, there's nothing here to multiply. So we end up getting just the 7 adds down. Then the negative 5 multiplies the 7 and we get negative 35. Add it down and we get negative 35. We talked about synthetic division and why it all works this way. Basically, the way it boils down is we switched the sign that was on the 0 coming from its linear factor, which was x plus 5 equals 0. And in doing so, that allows us to then add all of the numbers in the column rather than subtracting them. We also always are engineering our first column numbers to become 0. So, like, why bother, right? We don't need to write those. And we don't need to write a lot of other stuff in synthetic division. Again, we don't need to write the quotient because it's going to show up right here, right? What are we multiplying by every time? So we start with 7. We get negative 35. Multiply by negative 5 is going to be a positive 167. Sorry. 5 times 3 is 15, so that's 150. 150 plus 25, yeah. So positive 175. Cool. Now multiply by 5 again. Maybe I shouldn't have done negative 5. Negative 2 is nice this time of year. So if we multiply by negative 5, this is a negative. Let's see. 5 times 200 is 1,000. And then we're going to make the number smaller by 25 times 5, which is 125. So 2,000 minus 125 it's going to be 1875. And it's negative. Is a negative 1878. Alright, looks like we'll just get out the calculator. For ease of doing things and spending more time on better stuff. 1878 times 5 is 93. 90 minus 1 is 9389. 9389 times 5. It's going to be a negative 46,945. And that's also negative, so negative 46,950. Times 5 is going to be a 234,000 750. And now 6. 234,756. That is the remainder. If you need further reason why that's the remainder, right? We started with an x to the 6th. And then this was x to the 5th, x to the 4th, x to the 3rd, x squared, x, and now constant. And when we divide by a linear factor, that's x to the 1st. So now our quotient is going to have x to the 5th, x to the 4th, x to the 3rd, x squared, x, and constant, which leaves this last one as the remainder. And this means that p at -5 is equal to 234,756. And if you don't believe me, you can always go over to Desmos or plug it into your own calculator or whatever. Don't use ChatGPT for this stuff. It's too easy. Okay. It's also interesting is what would happen if we did, in fact, multiply by both or divide by both factors in a quadratic. What is that doing? I'm trying to think if that would like be anything in particular, or if it's just kind of not anything. I don't think it has any bearing on what we actually want, but nonetheless. Right. Factor theorem is then going to say that k is a 0 of p x equals k. Of p of x equals 0. If and only if k minus x minus k is a factor of p of x, right? Or what we really mean by that is that the remainder of p of x over x minus k is equal to 0. Some other bonus stuff, right? Rational roots theorem.
Can't get enough of your song of the moment? Download and indulge in the tracks you love over and over again with Spotify Premium. Tune in to discover an ad-free music listening experience where you can play your favorites in any order. Tap the banner to learn more.
I like lowest. Simplified. Simplified fraction form. S over t, x equals s over t, where s is a factor of a sub 0, and t is a factor of a sub n. So before, what we'd had we don't know if there are any rational roots, but if there are any, they will have to be of the form. Okay, the constant coefficient is a 6, therefore its factors are 1, 2, 3, and 6. And the leading coefficient is a 7, and thus its prime, doesn't have to be prime factors. Its factors are going to only be 1 and 7. Okay, and these can be positive or negative. But that means that we get plus or minus 1, 2, 3, 6, or 1/7, 2/7, 3/7, 6/7, and that's it. Right? There can be no other rational zeros of that 6th degree polynomial. So one of the things that we can do is then check it on your graphing utility or whatever. If we go 6x to the 6th minus 3x squared minus x squared. No, 3x cubed minus x squared minus 5x plus 6. There are none. Right, so we get literally no zeros. Demonstrable fact, just looking at it right here. We could also then zoom out just to make sure, but yeah, it's not coming back, man. Let it go. So anyway, we don't have any zeros at all. But this was just saying if there are any rational zeros, they must be one of those numbers. Turns out, yeah, we don't have any this time. Oh. I just changed my mouse sensitivity and I didn't even notice. So we get our rational roots theorem. We can also get our fundamental theorem of algebra. Which, very fundamental. The idea here is that an nth degree polynomial has n complex zeros. Now, keeping in mind that by just saying complex, this does include real, pure real, pure imaginary, or mixed. So pure real is stuff like 1, 5, 27. Pure imaginary is going to be 36, I, negative 7i, all that good stuff. Mixed is going to be stuff like 1 plus I, 3 minus 7i, all that good stuff. And I should probably change the color on those. So, what we just looked at with the 6th degree polynomial up there is going to say that that will have 6 complex zeros of some form or another. We've just found out that there are no rational zeros. We graphed it and found out that there are no real zeros either. So, no pure real. So there's going to be either pure imaginary or mixed complex numbers. We don't know. So we're going to have to take a look at that when we get back, potentially. Let's take this and copy it and then go to Wolfram Alpha. Gross. Yeah, notice that there are 6 of them. It was only showing 5. Which I was like, nope, hang on. Because the first 2 pair, the second 2 pair, and the third one's an odd? No, that doesn't happen. So we get this other one here. Notice that they are symmetric about the real axis. That's an interesting quirk of zeros of even degree polynomials. Usually they're symmetric somewhere unless they've been rotated a partial amount. All right, I will be right back. I'm gonna grab stuff. Maybe a small snack or something. So, be right back. Thank you for just something. Thank you for sticking around, and we'll be back in a little bit. Thanks so much, everybody. This is fine. Welcome back from break. um, yep, okay. Man, is Twitch acting up? Can't even tell. I mean, often, usually. Can't tell if it's acting up this time, or if it's just me. So yeah, we were looking at this. There's a very good reason, right, that this is going to be symmetric for even degree, and in fact, any polynomials are going to be symmetric about their real axis. All of our complex, non-real zeros come in conjugate pairs. So we end up with this negative 0.874149 minus 0.618712i, and negative 0.874149 plus 0.618712i. So we see this all the time in all of our polynomials we're always going to end up having these zeros which come in conjugate pairs. So when you're actually solving the polynomials themselves, then we're going to end up with that structure which just always exists. If it is an odd degree polynomial, then you're going to have some number of conjugate pairs, and then there's always going to end up being, if they're all complex, asterisk, right? Any that are complex non-real have to have a conjugate pair. So if we do a 5th degree polynomial, we can only have up to 4 complex non-real zeros. And then that 5th one has to be real. And that also makes sense if you think about it in terms of like the graphing. If we're graphing a 6th degree polynomial, then what you all saw earlier, where we end up with stuff that's all up here, is perfectly possible, right? It might never cross the x-axis. It's just staying up there. It could cross it once and then it has to come back. So that would give us 2. It could go through, tap the axis, and then go back through it again. That's 3 distinct locations. As it turns out, right, the one that is going to hit it and then bounce and come back has to be a double root, right? If it taps it and goes back, it has to be a double root. We could also have like a 3rd degree polynomial at that location, at which point it curves up, goes through it, and makes like a locally cubic area that looks like that. We could also come up with something that has just locally linear stuff. So it goes all the way down through this, does a bunch of stuff down here, and then goes back up again through here. So it only has 2. But, right, it will have an even number of roots that are represented. Again, some of them might be duplicated, but always ends up being an even number. I mean, that kind of goes into some combinatorics as well. So, if you have ever seen the bridges at Königsberg, that's a famous problem where there were a bunch of islands that were connected by bridges in Königsberg, and it's Leningrad now, right? I think. The task is to cross every bridge exactly once and get to all of the locations, right? All of the land masses in the area. The problem is that it turned out it's impossible because if you do a network map, then you end up not being able to actually hit every single location, every single node, without either revisiting a node or crossing the same bridge twice. So it always ends up failing us in that way. Right, random aside, right? Something like this. There's a bridge here, there's a bridge here, there's a bridge here, bridge here, bridge here. Maybe one more. Either way, this will work. So yeah, you try to go over all of the bridges and reach all of the land masses. And no, that didn't work because we could just go like that. technically this does reach the central landmass again, but at the same time, like, you went over all the bridges first, so you win. Now what is it? The nodes have to have two odd numbers or something like that. I think this also. Yeah, that's better. So we have, if we try to go through this one, right? Like even if this is allowed in the first place, I think we can assume that it is just, you know, you're visiting a different part of that island. I don't know, something. In this case, right, we can't do it because we end up visiting, or we end up missing one of the bridges. And it turns out that there's no way that you can actually get all of those bridges because you always end up locking yourself back into a certain place. Hey Fizzbuzz, how's it going? Caught you yesterday, I think. I don't know whether I was actually vocal in chat or not, but whatever. Welcome back in. There we go. So yeah, we did, there's some interesting stuff going on with the bridges at Königsberg. Again, the idea is that you can create like the land masses to be nodes. And then you have all of the bridges be represented by lines. They go to both, yeah. And again, the idea is that only one of these locations can have an odd number, I think. Because the problem is that if you... Yeah, if you start at 1, then we could just do this, come back to this one, use it again, and go through. That's fine. But now, if I try to do that again, right, what happens if I go here? Well, if I go this way, then we're stuck. We've already used all of the bridges. So that doesn't work. If we go this way, then we can come back this way, but now we're stuck, and we can't get all the bridges because we can't get that last one. So either way we go, we end up at a dead end because we have more than one node that has an odd number of connections to it. So anytime you see an odd number of nodes, start there. And then maybe you can end at a different one. That's the idea. I think that's how it works. Whee! Or is it just literally more than 2 is a problem? Might just be literally more than 2. Anyway. Tonight we are hashtag not sponsored by Vault Cities Caught in the Rain. Pina Colada Sour. If you like a Pina Colada. I listened to that song when I was about, I mean, I listened to it a number of times, but I finally listened to it when I was about 16, and after I'd had a first, like, serious relationship, and I was just like, oh my god. My parents are like, there it is. They were waiting for me to figure it out. Okay. Tastes a little bit, actually. I mean, it just pretty much tastes like pineapple. But I had at some point made tepache, which is fermented pineapple. And like you just take a whole bunch of pineapple chunks, mash, use the mashed up crushed pineapple or chunks or rings or whatever you feel like. Like pour the entire contents of the can into either a large jar or like a bunch of little mason jars. Mix it with a bunch of water and a bunch of sugar, and then you just like leave it in the back of your fridge. And it actually came out really well. You have to be careful because if you let it ferment too far, oftentimes if you just like use brewer's yeast, that'll jumpstart it pretty quick. Naturally, it's what it's meant for. But if you just like let it sit in your fridge, it'll ferment by itself. It's one of the problems with fresh pineapple is that it will just ferment sitting out. But if you get it timed right and you eat it or drink it during like a certain window, then it'll run out of sugar, have, a mild alcoholic effect to it. And if you let it go too far, it turns to vinegar. So you have to like balance it a little carefully. It's kind of interesting. And like fermenting fruit is a real easy way to introduce yourself if you're trying to like get into home brewing and just be like, I wonder if I could do this. Like, try it out. It's kind of interesting. All right. Yeah. In legal age of majority in your region. Okay. So not only will a complex roots have conjugates, but also any radical roots need to also have conjugates. So we had discussed actually, that's not even true. It doesn't have to be real. Any complex root. That is not rational and real. Will have its conjugate as another root. So what happens is if we end up with right, a plus it doesn't even matter. Root a plus root b, where a and b can be any real numbers at all. Positive, negative, other nasty things. is a root will imply that x equals root a minus root b is also a root. In theory, it could potentially also be the negative of that, but in theory. That's another interesting claim that's just kind of been made. Not A. Okay. Okay. So if we're trying to get the understanding of what all these terms are going to be, we said that P of x is going to be a sub nx to the n plus a sub n minus 1 times x to the n minus 1 plus dot dot dot. Plus a sub 2x squared plus a sub 1x to the first plus a sub 0. Okay, when we look at this, in order to get the polynomial multiplied back out, the highest term is going to be the a that's out front multiplied by only the x's throughout the whole thing, and it's got to be equal to a sub nx to the n as the first terms. Therefore, if we're just pulling out a number at the beginning and leaving k1, k2, k3, etc. to be zeros, then that a out front needs to be a sub n. Okay, and if we're looking for the product of the roots, then that's the product of only these numbers here. And then the a sub n is going to be along for the ride when this happens. That is then going to get us a sub n times negative k1 times negative k2 times negative k3 times times negative k sub n minus 1 times negative k sub n. Right, constant term. So we end up with a sub n, but then we end up with negative 1, right, raised to the, how many terms are there? This is just counting up. 1, 2, 3, all the way out to n. If we get just negative k1, then there is 1. Our n would be 1, and we would get a negative number. If n is 2, then we would get negative k1 times negative k2. There are 2 values there, both of which are negative, which multiply to become positive. So negative 1 squared becomes a positive number. We're good. Right, and then this is multiplied by k1, k2, k sub n minus 1, k sub n. This is the constant term, which is telling us that this is a sub 0. Okay, now we divide through, and we get that the product of all of our k sub i's, where I goes from 1 to n, is going to be equal to a sub 0 over a sub n times negative 1 to the nth power. Whether that's on top or on bottom, it doesn't really matter. This puts it on the side, right? Multiplying by a negative number anywhere isn't going to change it. It's still going to be based on the number of negative numbers that we have. So whether that is even or odd. An even number is going to get us to have a positive value, and an odd number is going to have us get a negative value. Okay. Cool. I like it. Surprisingly. Excuse me. Okay. Sum of roots, I think, is going to be done the same way, except we have to choose k sub I, whatever it's going to be, right? Each one of them exactly once. Because if we let it be any other number, then we're going to have a product of more than 1k. So the ones that only count one k value are the x to the n minus 1 terms, coefficients. So that says that we're going to get a sub n minus 1 is equal to okay. This is all p of x, not just that one term. So a sub n minus 1 is going to be equal to a sub n times x to the n minus 1 times, now we get the summation of all. If it's only choosing one of the k's, then that k is going to have a negative in front of it. So it will always be negative. And then it's going to be the sum of all individual k sub I. I goes from 1 to n. Alright, if we're including x to the m minus 1 there, then it goes there too. So this is not there. This is not there. A sub n minus 1 over a sub n. Move that negative over here is equal to the sum of all k sub I. Bingo. Woo. Okay. Good times. Where are we? Find the monic cubic polynomial p of x that has real coefficients such that the equation p of x equals 0 has roots 1 and 2 minus I. Right, so p of x is going to be equal to, this says monic. So this says that means that a sub n is going to be equal to 1. Sorry. Okay, this is going to get us x minus 1 and x minus parentheses 2 minus I. But that's not it. Because since it is monic, nope, not true. That's already taken care of here. Because there are an infinite number of correct answers here, if you did not say monic, right? A could be any value. They had to restrict that by saying, okay, let this be just the one with a sub n being 1. You could include any value that you wanted here. So either given a point that it goes through, in which case you'd have to solve for a sub n, or, you know, a sub n is equal to 5. Show us what the equation is. Okay, by the conjugate zeros theorem, this is telling us that x minus parentheses 2 plus I is also going to be a 0 of this particular function. So p of x is going to be x minus 1. Here, it's going to be x squared plus if we were to multiply x by the other one in both cases, then we end up with a oh, that's real. Okay. Oh. Okay, this is going to be a single x multiplied by 2 plus I, 2 minus I. No, that's the other one. It's going to be a negative.
Spotify Premium is the best way to upgrade your listening experience. Enjoy your music fully when you play songs in any order. Download them offline.
Okay, plus the product of them. 2 minus I, 2 plus I.
Tap the banner to learn more.
End. Okay, x minus 1 times x squared. Here, we're going to get a 2 plus a 2 is going to be 4. I minus I is 0. So 4x, and it's negative. So minus 4x. Okay, this is going to be a 4 times, right, negative I times 2 and I times 2 are going to be 0 when added together. And then negative I times positive I is going to be a negative I squared. I squared is negative 1, and so that's plus 1. X minus 1 times x squared minus 4x plus 5. Okay, x minus 1, x squared minus 4x plus 5, x cubed minus 4x squared plus 5x, minus x squared plus 4x minus 5. Okay, so p of x all multiplied out together is going to be, along the diagonals, they have the same number of x's, so we're just adding up like terms. So x cubed minus 5x squared plus 9x minus 5. Plus 5x squared plus 9x minus 5. Right, so again, 1 comma 0 is going to be a 0 of this particular function, and then we don't see anything else. Which again is pretty obvious from here. Okay. Let's probably call it for the night, and let's head over to, I believe, Rhacodactylus. Tonight is, he's been up for 4.5 hours, though. Currently doing speedrunning and science. Ancient Cave, any percent. I can't remember what. Final Fantasy, maybe? He's probably done with that. And the next part is a scientist speaking out. So I think that's what he's working on at the moment. Looking at the Lancet. How and why academic medicine must champion diversity, equity, inclusion, and accessibility. So we're going to head on over there. we're going to be back on Friday. Maybe tomorrow or Saturday if I feel like it. And we'll see how things go. So I hope to see you all soon. Have my YouTube channel almost forgot, right? At Obi-Wan Pez and at nsimplexpachinko6542. Obi-Wan Pez is the gaming channel, and Pachinko is the math content channel. So that's all over there. And hope to see you all soon. My name is Obi-Wan Pez. This is nSimplex Pachinko. Thank you so much, everybody, for stopping on in. Zach, Fizzbuzz, awesome to have you in. See you all soon.